Hi everyone, so thanks for joining me on yet another tutorial on utilizing the MDS Onto framework as well as the FAIRLinked Python package to transform your data sets from proprietary software into liberated ontology-aligned RDF data sets. Now, I'm just going to quickly give a tour on the package and then we'll get talking on the usage as well as what I did to arrive at the RDF dataset. Now, what I have here right now are two ontologies. This one's the XRD ontology, which I have been talking about with my previous videos, so you can have a look at them to see how I write with them. So this contains my leaf nodes, right? So I like to say leaf nodes because some of the terms that are in this ontology, they do not have any children. That means that it does not have any more subclasses. So these are the terms which I would like to collect data on, such as stack number, for example, log file, and so on and so forth. So I've talked about it extensively in my previous videos on how I arrived at those ontologies and what I did as post-processing to make sure that it is logically sound. Now, I created the low-level ontology. Now, that is not enough, right? We need the combined ontology as well. So I went ahead, generated the combined ontology as well. So what this combined ontology has is all those terms that I talked about as leaf nodes, as well as its path that traces itself all the way up to the top level MDS onto concept, which means, let me just pull up the onto alignment. Now, so imagine the ontology that I talked about with XRD is somewhere around here, right? In this layer. Again, there might be n number of layers depending upon how many domains and subdomains you have. But let's just assume that I have an ontology which is at this layer. The combined ontology would contain the path which traces all the RDFS subclass off as well as SKOS broader until you hit a top level onto concept here, right? So that is the reason why I need that combined MDS onto it. Now, again, some of you might have questions like, do I need the aggregated ontology, which includes all of the domains and subdomains that we've been calling MDS onto? No, not necessarily. You don't need it. You just need your leaf ontology, like I like to call it, which contains the terms that you would like to collect data on, as well as its path of using RDFS subclass and SKOS broader all the way until it reaches here. So this basically means your combined MDS onto contains the top level MDS onto concept terms, as well as your path towards reaching them via subclass of as well as SKOS broader. I hope that becomes clear, and I'll also share the ontologies that I have created just so that you guys could have a look at to see how that path kind of traces itself to the top level MDS onto concept terms. Now, let me pull up my terminal and then I'll start running the package, right? So I've created a folder. So I have two subfolders within this. It kind of like follows with my idea towards this demo. So in each folder, I have like two ontologies within them. Again, one of them is the low-level XRD ontology. The other one is the combined MDS onto. So without further ado, let me go into the first one. I'm going into the final. Just take this off. It's kind of confusing. So, all right. All right. Sweet. So I'm gonna go into the final name. So as you guys can see, those are the two ontologies here, which will serve as an input to the FAIRLinked package. So now I'm just gonna run FAIRLinked here. If you guys would like to know whether it already has been installed, you could just do pip list grep FAIRLinked, for example. And then I have currently installed pip installed the version 0.1. Version 0.2 is going to contain a lot more features. I would talk about it at the end of my video, but let's just get started with using the package, right? Cool. So FAIRLinked, Just run it like that. And then it should say, hey, welcome to FAIRLinked. Do you have an existing RDF data cube dataset? Okay. To answer this question, right, have you ever created like a RDF data cube dataset using this package? If you have, you say yes to this question. If not, this is your first time using this package, say no. Am I running an experiment now? So imagine you're going to your lab, you're gonna do like a bunch of different experiments, right? So am I gonna analyze samples right now? Like, am I gonna take measurements on them and all sorts of stuff? Am I gonna do that right now? Let's just say yes for now, right? I'm going to do an experiment now. It asks you these questions. Do you have these ontologies? That is the lowest level as well as the MDS combined. Now, if you answer no to this question, it is going to give you the default template. This is going to be applicable for people doing stuff beyond material science because typically this package kind of uses the MDS onto framework. So if you would like to use this package for your domain as well, you might want to take a look at the MDS onto framework and kind of adopt it to the domain that you're using so that all the tracing the path kind of works fluidly with this ontology framework that you have as well. So in this case, I'm going to just say yes for now. And then it asks for the path to the lowest level MDS ontology file. In this case, it's the XRD file that I have. So I'm going to just put in the um, path to the XRD ontology, and then I'm going to put in the path to the combined ontology as well. So I'm just going to put it in. Now, see, the reason for showing this ontology is because I'm going to say that this particular term, detector name, for example, right? I intentionally left out the mapping all the way up to a top level onto concept term. So that is that yellow bubble that you guys just saw. It did not have a path from the lowest level leaf node, which is MDS detector name. There was no path which reached top level yellow bubble concept. So because of that, this was ignored. But the Excel template was generated with for the namespaces as well as for the data ingestion. And then FAIRLinked kind of exits. So let's just take a look at the Excel template which was generated. I'm pulling it up right now. Give me a second. All right, cool. So this was the template that was generated for data ingestion. So as you guys can see, detector name is not indicated as a column. However, all the other terms that I wanted to collect data on, right? These terms or the leaf nodes had a path which traced its way all the way up to a top level onto concept term. So that's why you have these here. You can go ahead, fill in your data, and then all your metadata as well, including alternative names. So this is where you put in the kind of names that you want to call it. For example, stack number, right? You could just be calling it SN, for example. So that's how you would like to address it. And then in the RDF, that would be indicated as an alt label. And then if you have units, you would want to check out QUDT typically to figure out the units that you want to use for this particular data set. And as well as if it's a measure or dimension, measure means it refers to the actual value that you're measuring. For example, something that has units. Dimensions are typically like categorization. For example, let's say at a particular location, I want to measure the soil purity, right? So soil purity is the measure in this case, and the location is the dimension, all right? So that is the difference. And if you already have a URI for this particular column, indicate it like MDS instrument ID. So, which means you've probably declared a URI for this particular column, for example. Let's say you don't like MDS tag number, right? Which is what it typically gets labeled as. And you would want to use something like, which is already out in laser powder bed fusion, for example. You could just indicate as laser powder bed fusion and then indicate like it has a stack number. I don't like MDS stack number. I prefer laser powder bed fusion stack number. Why don't you use this URI? Because once I generate my data, I want to resolve the term to laser powder bed fusion stack number. I don't want to use MDS stack number. You are free to do that as well. So at the end of the day, we want to make sure that the terms that we're using to define our data, right? It is well defined such that it resolves to a particular URI out on the internet, and people can always look at what it defines at, what it resolves to when it comes to its meaning, what it's related to, and all of that cool stuff that I like to call as Linkipedia, for example. So that is roughly it. So it generates that particular template. I'm not going to save this. I'm also going to pull up the namespace template because I just want to show you guys what goes beneath of that stuff that we do with FAIRLinked. Just give me a moment. It's kind of taking a little while. Right, so just a second. It's getting ready. It's kind of hanging right now. What a time, right? Okay. All right, I'll come back to namespace in just about a bit. So my main purpose with this is to show you guys that if you have a term which does not map to a top level category, it will come up as a warning and it will prompt you to address it. And that way you could figure out a mapping so that it is also properly aligned to a top level onto concept term. Moving forward, let me just go back to the other folder, which I have the same ontologies, the same two ontologies. It's just that I managed to include a mapping for MDS detector name all the way up to a top level onto concept. So I did that. And I have the same few terms and a bunch of mock data as well to show you guys what happens as well. Now, I'm going to run FAIRLinked again. It's like, do you have an end? No, I don't have it. Are you running an experiment now? Yes, I am. And I'm gonna supply those paths right now. So I'm just gonna supply the corrected path. Oh, sorry. Yes. Lowest one is here. Also combined one. It's right here. This time you guys don't have a warning, which means that all the different terms that I wanted to collect data on, they have a path all the way up to that yellow bubble that I talked about previously, which is your top level MDS onto concepts, okay? Once it does that, it generates the namespace template as well as the data template, right? So as you can see, you would see the data template, which was generated, and the namespace template, okay? So let me try to pull that one up. I just hope it's not hanging at this moment. Okay, it did not hang, thankfully. I'm just gonna open. In and all right, cool. This time Excel managed to work. All right, so as you can see, detector name should be here. Yes, cool. Detector name is right here, right? So previously you guys saw that I did not include the mapping in ontology for detector name a path, which traces itself from the lowest level ontology all the way up to a top level onto concept, right? So now I managed to include it, and this is the data ingestion template. Again, if you want alt labels, you could put in your alt labels here. If you have units, do feel free to put in your units here. Indicate if it's a yes or no, depending on if it's a measure or if it is a dimension. And then if you have a URI which you would like to use, also put in those here. Okay. Now I kind of like did that already, but I also show up the namespace template as well. So this is that namespace template that was given. The reason for giving you these is to show that these are all the default namespaces that I have kind of programmed to be a part of FAIRLinked package. Now, you may or may not want some of these. That's totally up to you. There's no need to delete if you do want some of these. But again, if you feel that some of the namespaces, for example, MDS, right? Right now we are using this namespace. In the future, if this particular namespace wants to be changed, you could always change it here, okay? And it is critical that you do that so that you know the URIs work. And then when you click on a particular term, and then it resolves to a meaningful a resolution that talks about its definition, similar terms, and all of that cool stuff that we want to do with it, okay? So if you want to add more namespaces, right? You could always do that by appending like new namespaces and give its base URI here, okay? So I just wanted to point that out, and we have no more work with the namespace. So typically, most likely, you would not have to change much of namespaces because I've kind of included most of the common ones that we use. It's mostly this data template that you would have to add your data to and indicate all of that metadata associated with your data as well. So I'll show you this mock data that I've had it to the data template that was generated. And here you go. Nothing too complicated, you know, like really simple data that I've added to it. Just 5 rows of experimental data. Very simple, stack 1, 2, 3, 4, 5, and all of that, you know, measures and have like a unit associated with them. So this is important, okay? So every time you have like a measure, which is indicated by a yes, make sure to indicate units because you want to quantify your measures. And also, for example, some people like to call different names for their these standard terms, right? So these are the column variables which were pulled from the ontology. Those leaf nodes that I talked about extensively. So these are those leaf nodes and their naming convention. Now, you may or may not like these terms, and you would also want to associate them with the name that you want in your data set, right? So this is the alt label that you would want to associate it with. For example, log file, you can call it log file name, image sequence identifier, stack number, blah, blah. And some people like to call experimental station, research facility, for example. So these are all the alt names, right? So I've included those as well. If you use a different ontologies term that you would like to refer to, you could always do laser powder bed fusion image sequence, for example, okay? So just make sure that this resolves to something meaningful because that's something that you would want to achieve in your data set, and make sure that your data set is meaningfully represented in RDF. So that's it. I'm not just gonna do anything much to it. So I just want to show you guys how I populate data and all the metadata that I associate with the data that I have. Okay. So I'm gonna pipeline this through the package. I'm gonna call FAIRLinked. It's gonna say, do I have an existing RDF data cube? No, I don't have. Am I running an experiment now? No. So this is the time when we have completed our experiment, right? So I want to say no, I don't have an experiment. So it asks for an ORC ID. So what I'm gonna do is I'm gonna figure out my ORC ID right now. It's gonna say, hey, ORC. Sweet. So what I'm gonna do is I'm gonna take this last bit right here, and then I'm gonna put it in my, or oops, did not copy properly. Okay. So copy. Okay. Nice. Namespace template is right here. So I'm just gonna say blah blah. Data template. I'm gonna use this mock data, right? So I'm just gonna put this here. Output folder. What do we want to call our output folder, right? So I'm just gonna call it XRD demo right now, okay? So it creates the folder and then give it a name. For example, I did receive feedback that we do not want to have like a name for the data set and stuff. So this will be resolved in version 0.2 of the package, where we kind of address these feedback and keep the feedback coming so that we could always address them. So in this case, I'm just going to say sample XRD uh, data set, for example. Okay, so it kind of did the conversion, and here's what it did. It created a folder for you where it stores the data set. It created another folder. So let me just quickly pull this up to show you guys how it works. So here it is. So this was the parent folder that we were working with. We kind of like did all that, cool stuff with the ontology as well as the data population. After that, what we did was we provided a path to create an output folder. And then if you have a different output folder, you can always give a path to it. I created this folder, and then it created a folder which contains all of that RDF stuff. All right. So you have the turtle file. You also have the JSON LD representation of it, and it also creates a SHA-256 of it. So it's just a hex digest of your turtle file. Okay. This is just to tell you if something has changed. You could always compare the SHA-256 hash of your turtle files to see if something has been changed or tampered with. And I'm just going to quickly open up this turtle file to show you guys what goes beneath that RDF conversion. All right. So again, this is not something that's alien to us. This is the prefixes. What we have created is we gave the data set a name, right? So this is that name. It says that I have a sample XRD data set, which is of type a data set. This is the cube vocabulary, which refers to the RDF data cube. Here's the URI for it. And it was created by me. So I just put in my ORC ID in here. And the title of the data set is sample XRD data set. And this data set contained 5 rows, right? If you guys recollect that, I'm just going to pull up the sheet real quick again, just to show that. So this was the mock XRD data. So I'm just going to pull up the template, and then we can sort of compare side by side, right? Okay. So you guys can see that, there were like 5 rows. Oops. Yeah, right here. There were like 5. Okay. As you guys can see, there were like 5 rows of experimental data. So what I've done is that I've created 5 slices to indicate those 5 experiments. It could be 5 samples, depending upon how you like to call it. But essentially, these are the 5 experiments. This is to give you like the schema, right? Like, you have a data set. You need to know what goes into that data set, right? In this data set, this guy created it. This is the title of the data set. And this data set has 5 slices or 5 experiments. And then it follows this structure, which is described by MDS data structure definition. Okay. Now, this is the data structure definition. It basically tells you what are the different columns in your data set. Okay. So measure type is something that is inherent to RDF data cube. It tells you what is the measure that you're looking at in a particular observation. I would encourage everyone to read up the RDF data cube W3C standard, which is published. That would help help bring you up to speed on what is the RDF data cube and what goes into representing your data in terms of RDF data cube. Okay. So I've defined that I have a dimension, which is image sequence. So I go back to this data set again. So image sequence, right? Is it a measure? No, it's a dimension. So that's why it is defined as a dimension here. And look at measure, right? MDS wavelength. Let's look at wavelength. Is it a measure? Oh, yes, it's a measure. So that's why, oops. All right, so that's why it is labeled as a measure. And likewise, it is done for every single column which is represented in here. And then I want to talk about what goes beneath the alt label part, right? So you see that data detector length here, right? So let's look at detector length, for example, right here. Detector length is defined as a measure, and it is also having an alt label of detector space length, right? And then it captures that it belongs to the category recipe. So as you can see, your detector length is right here. It is mapped all the way up to recipe. So this is crucial when it comes to SparkQL queries. So you could do like a bunch of queries. Show me like what is the category of this particular measure or dimension, and that way, it could speed up your analysis. So that's the reason for including it as part of the metadata about the variables, right? So this experiment slice key, it typically indicates like what goes into the dimensions. So if let's just pull up this. So experiment ID, is it a measure? No, it's a dimension. And so is facility. Let's look at facility. Facility is a dimension. So all of these stuff, right? These are all the dimensions. It's just to tell you guys that instead of repeating, right, for every single observation, all the different values for all the dimension, this just to tell you guys that, hey, you don't have to repeat all the dimensions, and these are essentially captured in the different slices, for example. So let's look at slice experiment one, and then we can talk about it, and it becomes a lot clearer. Okay, so let's just look at experiment ID one. Okay. So in this, it follows the slice structure as defined by experiment slice key, which is what I just talked about. And it looks at detector name. Let's look at detector name. Does it match? Yes. So you have detector A, and then you have experiment ID 1, facility X. So does it map to facility X? Yes. It also has a file name referring to image. So this is the thing, right? So this is not just about converting your data sets into RDF representation. It is also about representing your metadata in its RDF representation. So there's times when you have metadata describing images, right? We produce tons of images, even for PV, for XRD, and all the different domains that we have. So when you have satellite images, for example, you could give like a path to the file, and we can kind of capture it right here. And then the rest of the stuff that's within this tabular data, right, is just going to be your metadata describing what goes into that particular image, right? So all of the other values are locked in place. So if you can just go through this file, I'll make sure to share it, and you can see that these matches. Now, the important part is that all those stuff that is being captured here, right? Those values that you see here, these are all the dimensions that we mentioned in the experiment slice key that I talked about here, which means every single experiment has these bunch of dimensions, and these dimensions values are captured when you define the slice for any particular experiment. So these are the values for the dimensions. Now, every single measure is treated as an observation. So if you notice, right, there are 6 observations. This means that this particular experiment has 6 measures. So let's just double check that that is the case, right? So you see that there is a measure 1, 2, 3, 4, 5, 6. So exactly we have 6 observations. So let's just look at observations 1 through to 6, okay? So if I look at observation one looks at measure, which is pixel size. So observation one looks at pixel size. Pixel size has a unit, which is micro M, and it also has the value 5e to the -1. So this is exactly what it is looking at, right? Likewise, if you look at observation 11, right? So observation 11, what does it belong to? Let's just quickly have a look at it. So observation 11 belongs to experiment 2. And let's just have a look at what it is looking at. Observation 11 is looking at energy. So it is looking at energy, and then it is belongs to experiment 2. So its value should be 12.6. Let's just see if it has 12.6, which is exactly what it has. And it doesn't have any alt label, so we can double check that it doesn't have alt label. And you can see that the unit is accurately captured right here, right? So let's just make sure that energy does not have any alt label associated with it. So let's just see if there's an energy in here. So energy, all right, okay. It's a lot of energy. All right. See, so since there was no alt label that you had mentioned, there was no alt label that was captured in here. So this is essentially how your data set is converted into its RDF representation. So right now, what I give you guys as part of version 0.1 of this package is I take this tabular data set that you have given me, whether it is data or if it is a combination of data and metadata, I take this and make sure that it is aligned to the ontology that we have come up with using MDS Onto. I break it down into giving a name for the data set. I also make sure that it contains all the various columns by defining what goes into this particular data structure. So imagine you're like curious about this data structure, right? You imagine you're curious about this data set. You could just query for the data structure definition to figure out what is exactly present in this data set, and then you could figure whether you're interested in this data set, right? So this is the part where all those automation pipelines come in. So when you're like looking at data set A, you can quickly figure out what are the columns in this data set. Am I interested in it? Look at the meanings of the different terms, which resolve to useful stuff out on the internet. And then you can figure whether I want to use it or do I not want to use it. Is it relevant to my purpose? So that's the automation thing that I've been talking about to fuel your data hungry AI models, like I like to call it. So this has been like a relatively long presentation, but I'll just quickly wrap it up. Just give me like a couple minutes. In this, you also get your JSON LD representation. So this is the JSON LD equivalent of that particular turtle file that we just saw. It also contains all your values as well for every single observation and dimension for every single experiment. Okay. The hash file, I just want to quickly show you guys what goes inside of it. Is just a hexadecimal representation of the hash of the turtle file. This is just, again, to show data integrity. That is, if anything has been tampered with, the hash will not match. Okay. And as of now, I created a single JSON LD and a single turtle file, which captures your entire data set as a whole. Okay. In version 0.2, there will be JSON LDs for every single row. That is every single experiment that you have in your data set that you have supplied the package with. So that is another feature that will be coming up in version 0.2, but this is just to tell you guys what goes into version 0.1. Now, let's say you converted your data set, right, like into RDF representation, but you want to get back the actual data frame representation of it, right? So you want to convert it back into like a Parquet file for storage, or you want to get back like a CSV just to look at the data and stuff. That is also possible. So let me go back to FAIRLinked. Let's just look at what we have here. Let's just not save it. So what do I have in here? So oops, let me just close all my Excel stuff. Okay. So what we have here would be the output folder, right? Inside the output folder, we have the RDF representation of things. So what I want to do is, let me just go inside of it. Mm, So in this naming convention, right, I appended the ORC ID, which I supplied, and this is also the timestamp. So if you run the package multiple times, right, each time you'll create a unique data set. That is because we want to make sure that the timestamp is also part to enable data stewardship. So that's just one part of the package, and let me just convert one of these back into its data frame representation, right? So let me call FAIRLinked. So this time I do have an RDF data cube data set, and this is either one of Turtle or JSON-LD. You could supply either one and it would still work. Yes. Enter the path to your blah blah. So I'm just gonna copy this JSON-LD for now. Output folder, I'm just gonna put in converted, yeah, for example. So the folder has been created, conversion stats. So it gives you that there were 5 rows of experiments, there were 15 columns, and then 3 distinct categories were found, which is result, tool, and recipe. And then it sort of gives you a preview or sneak peek into what is the first row. And then it prompts you with this question of, do you want to save the data frame into a CSV file? And then you could always say yes or no, but I just want to say yes. And then it kind of gives you that particular CSV as well. So if you just going to convert a data frame, for example, it gives you the Parquet file, And it also gives you the output CSV as well and the variable data metadata JSON. So I'm just going to open all of that and show you guys what exactly I'm talking about, all right? Okay. So this is where we left off, right? So we looked into XRD sample data set. We looked in the converted data set. So this is the Parquet file, right? And then we also have the output CSV. So I'm just going to open it real quick. So this is exactly what you had given the package initially, right? It gives you back the exact data sorted by experimental ID, and you can like compare these two data set. It will be the exact same. And I also have the variable JSON. So if I just open it real quick, which I just did, oops, it should pop up in just a bit. All right, so this is the metadata associated with every single column. So it tells you whether it's a measure, if it had an alternative label, and what was its URI. So technically, if you actually take this URI, put it out in the internet on your favorite browser, this should result to something that is meaningful. And that is the whole reason behind doing all of the conversion into RDF so that we can set up a whole bunch of automation pipelines which help us to reason over the data sets that we have to come up with, lots of inductive and deductive reasoning. Okay, so everything that you guys gave, which is, including the alt labels, it is all captured in here, and then the existing URI is also captured. Okay, so what you gave is also what you get back. So that is the end of this presentation. So this is all that is done with version 0.1 of this package. Version 0.2 will also be coming out with those row by row JSON LD conversion. And I look forward to seeing you guys again. Thank you.